Hello, today we're going to be talking about vector quantities and scalar quantities. These are both different types of measurements, and we're going to talk about the different properties that they both have. A scalar quantity is a magnitude only. And when I say magnitude, what I mean is a number only. Okay? Well, with a unit, because it's a measurement, so it has a number with a unit, but not a direction, which is what a vector quantity will have. So it's a number only. It's always positive. Okay? Always positive. Some examples of scalar quantities are distance, speed, length, mass, volume, energy, and the one that's probably the most important that I kind of left off the list, and that's time. Okay? You can't have any of these quantities that are negative. Okay, you can have negative energy, negative volume, negative time. All of them are always positive, and they always will have just a number with a unit. With scalar quantities, you can simply just add them together, subtract them, multiply them, divide them, and it doesn't change any of the properties about the quantities. Okay, so scalar quantity, magnitude only, so a number, it's always positive. And you can just add them, subtract them, multiply them, divide them like you would any regular numbers. Our other type of quantity is a vector quantity. And a vector quantity consists of a magnitude and a direction. Okay? So again, the magnitude is just the number. So anytime a question will ask you to solve for the magnitude, they just want a numerical value. The direction can be represented by lots of different things. We could have an angle. We could have a cardinal direction. Or we could have a sign. And the sign is what we're going to use most often in physics. We could have a positive direction or a negative direction. Most of the time, when we set up the signs, if we were to set up our Cartesian coordinate plane like you're used to in math, things that go to the right are positive, things that go to the left are negative, things that go up are positive, and things that go down are negative. Okay, the directions that you're used to. We're not going to change any of that stuff just because you're in a new class, so we're going to keep those things that you're used to. We'll use signs most often, like I said. With the first assignments we'll talk about some angles and some cardinal directions. So you have a number, and you'll have some kind of angle, direction, or the sign that represents the direction along with the unit when you have a vector measurement. So examples of vector quantities are displacement, velocity, acceleration, force, and momentum. It all starts with displacement. Displacement is a vector quantity. It tells you the direction and the change in position of an object, and we're going to talk about that more in just a second. But then velocity is based on displacement, acceleration is based on velocity, and force is based on acceleration. So then you have those all kind of build off of each other. But the thing that makes it a vector quantity is that initial displacement. When you have a vector quantity, and it's in two dimensions, you can break it up into what we call components. Say we have this vector, and when we draw vectors, we're going to draw them from the tip to the tail. Okay, the tail is the arrowhead. You're going to draw them so they are in the correct direction. And they are drawn to scale. Okay? When I say they're drawn to scale, what that means is that if you have two vectors, one represents a value twice as large as the other, then the length of that vector should be twice as great. So let's say we have this vector here, And notice that it is in two directions. It goes both horizontally and vertically. Okay, so it's in 2 dimensions. If we were to ever do some calculations with these vectors, what we would need to do is break them up into 2 one-dimensional vectors. The 2 dimensions that we are most commonly or most familiar with are the x and the y. So if we have this vector, we can break it up into having an x component and having a y component. Okay? So we have x component, we have a y component. If you're more comfortable with setting it up so it looks like a triangle, you can take this and just put it right here. Okay? But either way is correct. Either way is fine. It doesn't matter how you put it. Some people are just more familiar or more comfortable seeing it to set up a triangle. If we're given this angle right here, oops, we'll just call it angle theta, then we can determine what our x and y components are based on the length of our overall vector. Okay? So if we just look at this and we say that this is d, okay, and d is just going to be the length of our vector, we can determine dx and dy if we know a little bit of trigonometry and we know what this angle is right here. Part of your summer assignment was to look at these angles and determine what to be able to use trigonometric relationships to solve for different quantities. Okay, so let's go through our 3 basic trig relationships real quick. We have the sine of an angle, and the sine of an angle is equal to the length of the opposite side over the length of the hypotenuse. The cosine of the angle is the ratio between the length of the adjacent side and the length of the hypotenuse. And the tangent of an angle is equal to the relationship of the opposite side to the adjacent side. Okay? When you type in one of these trig functions and an angle into your calculator, it will give you some decimal value. That decimal does not appear out of thin air. It doesn't, not made up by your calculator. It is actually the ratio between the lengths of the sides to each other. So if we go back and look at our triangle over here, we'll see that this side right here, our x side, is the adjacent side to the angle theta. Okay? If theta is right here, then this side is the one that's adjacent to it. So here's theta. The side that is right next to it is the adjacent side. dy is our opposite side. Okay, and that's relative to that angle theta. So if theta is here, and across from it is dy, so that's our opposite side. And of course, our longest side here is our hypotenuse. Okay? So what we want to do is we want to be able to determine what dx and dy are based on the hypotenuse and this angle theta right here. So the first thing we'll look at is we're going to look at the sine function. So I'm going to erase everything real quick, and we're going to look at the sine function. Okay? We're going to use this problem as an example, and we're going to say the sine of theta equals the opposite side over the hypotenuse. Okay? So if theta is right here, and we want to find the sine of that angle for this specific triangle, we would plug in and we would say sine of theta equals the opposite side, which is dy, over the hypotenuse, which is d. If we then wanted to solve for dy, we just multiply both sides times d. Okay, they'll cancel out over here. And so we'll get a relationship for that length. If we just multiply the overall length of our vector, the magnitude of our vector, that's what the d stands for, numerically would be the magnitude, equals d times the sine of the angle theta. So that's where that trig relationship comes into play, being able to solve for the lengths of the sides of the triangle. If we then wanted to look at the cosine function, we know the cosine of an angle equals the opposite side, the adjacent side over the hypotenuse. So in our problem here, cosine of theta equals the adjacent side, which we said was dx, over the hypotenuse, which we defined as d. So if we want to solve for dx, we multiply both sides times d, and we get that dx equals d times the cosine of theta. So again, we're able to solve for that horizontal part of our vector by multiplying the overall length of the hypotenuse, the magnitude of the vector, times the cosine of the angle theta. And we'll get much more practice with this. Don't feel like you're behind or really lost if you don't understand it right now, but something you might want to look at. We said earlier that distance was a scalar quantity and displacement was a vector quantity. Let's go a little bit further into that and see what we can figure out. Okay, so let's put that on the board here and say that distance is a scalar. We know it's just a number with a unit. Okay, displacement is a vector. It's a number, a direction, and a unit. Okay, remember our direction can be an angle, a cardinal direction, or a sign, positive or negative. So we're going to have an object here. Let's just say it's going to go kind of winding path. Maybe a bug flying around. You know, you're trying to catch the bug and it just flies all around. And we want to determine what the distance and the displacement of the bug would be. The distance we could find by simply just tracing that line that the bug flew. We can add up that entire distance. That will tell us how far the bug has flown for our distance measurement. If we want to find the displacement, however, there's only 2 points we're worried about. Right here and right here. Okay? This point over here, where the bug starts at, we're going to call x naught, meaning x initial, the initial position. We're going to use x to represent position. So over here where the bug starts is its initial position. This point over here we're going to call xf for the final position. When we're solving for the displacement of an object, we're only concerned about x naught and xf. Where does it start and where does it finish? Wherever it goes in between really doesn't make a difference to us. It's just where it starts to where it ends. So if we wanted to then determine what our displacement vector is, we'll draw a straight line from x naught to xf. Okay? And that line right there, that orange line, is our displacement vector. Okay, so a little bit different idea for you. Think about your displacement during the day. In the morning, more than likely you're going to wake up in your bed, probably haven't spent the night anywhere, didn't fall asleep on the couch the night before doing your homework. So you wake up in your bed, get up, go to school, however many miles that is to get to school, come back home, maybe run an errand or two, end up back at the house, and right before you go to sleep, you're back in your bed again. Your displacement during the school day, or during the entire day, I should say, is 0 because you end up where you started off. You, of course, traveled some distance, and it took some time, but your displacement then is only going to be 0. Okay? Your displacement is 0 because the distance from where you started to where you ended was 0. Let's do a quick example here. The city bus travels 2 blocks east, 4 blocks north, and 1 more block east. Determine the displacement of the bus in terms of city blocks. So we're going to draw a diagram. Okay, we're asked to solve for the displacement. Okay, so displacement we know is a vector quantity. We're going to have to draw these in terms of vectors. So we need to be in the right direction, and they need to be to scale. Okay, this will make our life easier. It will allow us to draw a diagram that better represents our correct answer. One of the things in physics you need to do is always draw diagrams. It's very important. Okay, so we're going to start off with the initial position of the bus, which is going to be right here. It's going to go 2 blocks east. So we're going to draw a little line. Okay, put an arrowhead on it. That's going to represent 2 city blocks. The bus is then going to go 4 blocks north. If this is the distance of my 2 blocks, then my 4 block vector should be twice as long. So I'm going to try to estimate that as best I can. It's going to go up right there into the words. Okay. And that's going to be 4 blocks north. Finally, it's going to go 1 more block to the east. So I'm going to use my other vectors as scale, and I'm going to draw a 1 block vector to the east. Okay? So I've drawn my diagram. I have 3 different vectors, and now I need to add them up. Okay, we said before that direction was important. If you were to look at this picture and you want to find the total displacement, does it make sense to you to simply add up 2 plus 4 plus 1? Of course not, because the displacement vector that we know we have, or if we draw that one, it's from here to there. And we can tell, based on the scale that we've drawn, that is nowhere near going to be 7 blocks. Okay? And we also know, because it's a vector quantity, that we can't just add them together. So we're going to look at this, and we need to figure out a way to determine what that value is. Well, if we try to complete a triangle, okay, that's always a good thing. If you have a diagonal, it's always a good idea to try to complete a triangle to make your life a little bit easier. Okay, so I'm going to complete the triangle. I'm going to make one side down here. I'm going to make one side here over on the side. Okay? Can we determine what the length of this side is? Of course we can. We know that this part right here is 2, and we know that this part over here is going to be 1. So our overall length of this side is going to be 3. Our vertical side, our y side, we know is just this value right here. Okay, and that's a 4. So I'm going to go ahead and write a 4 over here to represent this side. I'm going to redraw my triangle just to make it a little bit cleaner. So over here I'm going to draw a triangle. Okay, we're going to have this side will be 3. This side is 4. And I want to determine what that is. What is that length? Well, if this is completely horizontal down here, and this one's completely vertical, what kind of angle do we have right here in the corner? That's right, a right angle. And if we know our 2 legs of a right angle, can we determine what the length of our hypotenuse is? Of course we can. Something that you've probably known a long time. And that's to use the Pythagorean theorem. The Pythagorean theorem says a squared plus b squared equals c squared. Remember that a and b are just the legs of a triangle, and C is the hypotenuse. It doesn't matter which one's A, which one's B, but it does matter which one is C. So if we plug this in and we say 3 squared plus 4 squared equals C squared, then we have 3 squared, which is 9, plus 4 squared, which is 16. We get 25 equals C squared. So then C is 5 blocks. Okay, so that gives us the magnitude of our displacement vector. Now we need to figure out what the angle is. So if I set this up, and we have our theta right down here, now we need to figure out what theta is. We're going to go back and use one of our trig functions that we used a long time ago. And we're going to use the inverse tangent. Okay, if we find the tangent of an angle, that's equal to the length of the opposite side over the length of the adjacent side. In this case, we know the opposite side is going to be 3. Okay, it's right there. Or, sorry, 4. 4 is the opposite side, opposite of theta. The adjacent side is going to be 3. So we know those two things. The thing that we do not know is theta. So we're going to plug in here, and we're going to set up our trig function, and we're going to say tan theta equals the opposite side, which is 4, over the adjacent side, which is 3. So now we need to figure out what theta is. And when you have a trig function, in order to figure out what the angle or the value of the angle is, you have to do the inverse of that function. Okay? So take your calculator right now, and I want you to plug in tan to the -1, which is the inverse tan. Okay? It's not tangent inverse. It's actually a function that already has that -1 in there. You don't want to have to hit tan and then -1. And you're going to determine what theta is. And you should get that theta is 53.1 degrees. So we'll say theta is 53.1 degrees. Okay? And so we've solved our problem now. We could say that the displacement vector is 5 blocks, 53 degrees, 53.1 degrees north of east. Okay, so that's how our correct, proper, full answer for the city bus is. 5 blocks, 53.1 degrees north of east. Let's do one more example, and we'll send you on your way here. An explorer examines a map to determine his best path to a hidden treasure. From his starting point, he figures he must go 4 kilometers east, then 6 kilometers at an angle of 30 degrees north of east. He finishes his trip by going 2 kilometers north. Determine the distance and displacement from the base camp to the treasure. Okay? So we're going to, again, draw a diagram. First part, if we start here, he goes 4 kilometers. Then he's going to go 6 kilometers, 30 degrees north of east. I'm just going to estimate real quick that 30-degree angle. Make my vector 6 kilometers long. And then he's going to go 2 kilometers north. We'll make 2 kilometers right there. Okay? So when we look at this, we can quickly draw a picture, or draw a vector, I should say, to represent the displacement that we've seen. So displacement will be from here to there. From starting point to ending point. That's all we're concerned about when we talk about displacement. X naught, X initial, to X final. Distance is pretty easy to find too. We know that distance is a scalar quantity, so we could just say the total distance equals d1 plus d2 plus d3. And so our total distance then, pretty simply, 4 plus 6 plus 2 is 12 kilometers. Okay? Easy enough. We can definitely handle that. Now we have to determine what the displacement is. What is going to be that numerical value? And to do that, we're going to have to complete our triangle. Okay? We just talked about that before, was completing our triangle. So we're going to set this up, and I'm going to draw a diagram here. Okay, I'm just going to kind of do my little dashed lines here. And now we're going to be able to complete our triangle. If we look at this, we know that part of our triangle on the horizontal side, we know this right here is 4. We know that on the vertical side, that this is 2. So the questions are, what is this side? Oops. And what is this part? Okay? So in order to do that, we're going to use those trig identities we talked about earlier to figure out what those sides are of that small triangle where the 6 kilometer vector is located. Okay, so I'm going to erase this distance because you already have that. That's easy. And I'm going to redraw that small vector. Okay, so we're going to draw a line here. This is 6 kilometers. This is 30 degrees. And we need to know this side and this side. And that'll allow us to complete our triangle and then use the Pythagorean theorem. Okay? So this is our adjacent side. Okay, so we're going to solve for dx. So we're going to say dx, we said before, equals d, the length of our vector, which in this case is the 6, times the cosine of theta, which in this case is 30 degrees. So we're just going to plug that in our calculator. And we're going to say 6 times the cosine of 30, and we get the dx. Let's go ahead and write that out just to make sure we have it all written down. Make sure your calculator is in angles, by the way, not in radians. Make sure it's in degrees. Okay, you get 5.20 meters. Okay, so that part right there goes here. So now we know that the total length of that triangle is going to be 9.2 meters on the horizontal side. Now we're going to do the same thing for our y side. dy, we know, equals d times the sine of theta. So dy equals 6 kilometers times the sine of 30. The sine of 30 is just 1/2, so nice and easy. So dy is going to be 3 kilometers. So we can take that and put it right here. So now we can redraw a triangle that will allow us to determine what our displacement is. Okay, so I'm going to plug those in. I'm going to redraw a triangle down here. That's our unknown vector. Very crooked line, I'm sorry about that. This side we know is 9.20 kilometers because it was the 4 kilometers plus the 5.2 kilometers. And this side over here is going to be 5 kilometers because it was the 2 kilometers plus the 3 kilometers that we brought in. Okay, so now we know the two legs of our triangle. If we want to figure out what the overall displacement is, then we're going to use the Pythagorean theorem yet again. Okay, so we'll say a squared plus b squared equals c squared. And we'll say 9.2 kilometers squared plus 5 kilometers squared equals c squared. So not as pretty as a triangle as we had earlier, but that's alright. Most of the time they're not going to be pretty triangles. And we've determined that c, in this case, is going to be 10.47 kilometers. Okay, so there's our numerical value, 10.47 kilometers. So the magnitude of our displacement, 10.47 kilometers. Now we need to figure out what that angle is because it's a vector quantity. So just like we did before, we're going to do the inverse tangent of the y side, the opposite side, over the x side. So let's slide this up one more time here. So we know tan of theta equals opposite over adjacent. So tan theta is 5 kilometers over 9.2 kilometers. When you do these kind of problems, you should use your common sense. Look at this angle. Is it going to be greater than 45 degrees or less than 45 degrees? Yes, it's going to be less than, because this side, the 5 kilometer side, is less than the 9.2. So the angle is going to be less than 45 degrees. So you should use that to kind of check yourself at the end. If you get a value that's larger than 45 degrees, you know you've done something wrong. Again, make sure that your measurement, your calculator is in degrees. And we'll get the theta here in this case. Inverse tan of 5 over 9.2. We get 28.5 degrees. So your correct answer then would say that the displacement of the Explorer is 10.47 kilometers at an angle of 28.5 degrees north of east. Go ahead and work on those two problems that you have to look at for the rest of your homework tonight, and we'll see you in class and answer any questions you have. Thanks.